I will start with my teaching philosophy. I've attended many universities in my life. The Warsaw University in Poland, the RWTH in Germany, the Kanazawa University in Japan. Now I'm at the University of Florida in the United States. I've seen different teaching philosophies and styles throughout my life. And the one I liked most was the one which encouraged the creative and independent thinking, which would say that there are multiple solutions for the problem we have at hand. There is no one solution in the textbook. Each of you can come with your own solution, which may be far better than the solution in the book. Let's set it as an open-ended question and try to answer it. And then if we can't, we can go back to the book and see what the book says. But start with own creative, independent thinking. And of course, fostering excitement and enthusiasm for science. Science is discovering new things, discovering answers. It's not doing homeworks. It's not, quizzes and gives them this feeling. I will showcase practical problems. So the ideal approach would be come up with the practical problem and ask the class, okay, we are going to solve that problem by the end of the semester. And I will guide you through the process. And who knows, maybe you can find better solutions than I can. Let's see. Let's walk through this. Outline feasible engineering solutions and encourage students to be fearless about asking questions. Challenge me. This is an example of the course I'd like to teach, but since I have very strong background in mechanical engineering, I can teach a whole array of courses, like undergraduate structural analysis courses or the finite element method courses. But this would be the course I would bring to the department, simulation techniques in civil engineering, and this is a course which I think is very much needed at the civil engineering departments, and it's not taught at all. People are taught to follow the codes, but if you ask them to do something on their own, they feel insecure, they feel lost. There is no guidance, no procedure, no recipe. What do I do? So to give you an example, let's say that the problem is, let's see how a steel beam would respond to an impact. If we design something and we want to see what is the response of of a steel beam, I give them the dimensions. This is the experiment, and we may carry out the experiment at the end of the semester, and let's see if we can predict it. So the first question will be, what is steel? What material model we are going to use to represent it? And there will be a whole array of materials, and we could use all of them and see which gives us the best response. I would personally recommend the large strain material model using effective plastic strain versus effective stress. Then we would simulate the static response, apply static loads, and either do experiments ourselves, or it's possible to find experimental data in the literature. So this is data from the literature. These lines represent the test results, and these lines represent the simulated results in the Dyna software. So then after they do the simulations, they see, okay, that's what I did wrong. Maybe I chose wrong integration scheme, wrong material model. There is feedback there. And then we can go for the impact and see if what is happening, what type of difficulties we encounter in the simulations. And of course, every simulation has to be verified with experimental results. This is experimental data from the literature, open literature by Norman Jones and Liu, and see how the students' work compares to these curves. So then by the end of the semester, students know how to perform such simulation on their own. And this can be different thing, doesn't have to be a steel beam. It can be a simulation of a small frame or a signal, traffic signals or something, but they have the experience, how to face the problem and how to proceed, how to verify the results. My long-term teaching goals will be, I want to educate engineers in both basic concepts in simulation techniques as well as expose them to real-life simulation case studies. So influence them so they become more comfortable in solving the problems on their own. If there is no code specification, how to solve the problems, they can try to use the basic engineering judgment and basic physics to solve the problem on their own. I personally believe that virtual experiments will replace the traditional make and break philosophy. And we can see it in the automotive industry, that people tend to use computers more and do the simulations more, and this is the trend. And industry demands students to know more and more in that field, and we have to produce students who have this knowledge. That's all what I want to say you, and I leave the floor open to questions.